Dewaxing is an important process step in the production of lube oil base stocks with low pour point. The feedstocks for dewaxing include deasphalted oil from the deasphalting process and heavy vacuum gas oil from vacuum distillation. There are basically two technologies for dewaxing: solvent dewaxing and catalytic dewaxing. Today, I offer the concept of adsorptive dewaxing that relies on entropy effects to exclude the longer chain alkanes while selectively adsorbing the shorter alkanes. I demonstrate the principle of exploitation of entropy effects for adsorptive dewaxing by considering two different adsorbents, LTA-5A zeolite and TSC zeolite. The all-silica TSC zeolite with a Tschörtnerite framework has the highest cage volume of any known zeolite. The presentation today is basically a follow-up to my video titled Exploiting Entropy Effects in Mixture Separations on my YouTube channel. I begin by explaining the concept of entropically based adsorptive separation for dewaxing by looking at the adsorption of linear alkanes with varying chain lengths in LTA-5A zeolite that consists of cages of a diameter of approximately 11 angstrom. Each cage is separated from adjacent cages by windows of 4.3 angstrom. If we look at the adsorption isotherms for normal C8 alkane, we see that the saturation loading is 2 molecules per cage, and indeed we see 2 NC8 molecules can be located within a single LTA cage. This may be popularly referred to as 2 snakes in one basket adsorption of NC8 in LTA-5A zeolite. For NC9 and NC10 linear alkanes, we can also locate 2 snakes in one basket, and the details of the unary isotherms are discussed in my paper published in Separation and Purification Technology in 2011. The 2 snakes in one basket adsorption holds also for NC11 and NC12 alkanes in LTA-5A zeolite. For the adsorption of NC13 alkane in LTA-5A zeolite, the saturation capacity is just 1 molecule per LTA cage. And we indeed see the snapshots that confirm that the maximum cage capacity for NC13 is 1 per cage. If we consider mixture adsorption of NC8 and NC13, and we plot the loadings per cage as a function of the total fugacity of the bulk fluid phase mixture, we see that at low total fugacities corresponding to the Henry regime of mixture adsorption, the absorption equilibrium favors the longer chain NC13. However, as the total fugacity of the bulk fluid mixture increases and the adsorption occurs under saturation conditions, say at a total fugacity of 100 megapascals, the mixture adsorption equilibrium is entirely in favor of the shorter NC8, and the longer chain NC13 is excluded from the pores because it loses the entropic battle. The details are provided in my 2011 paper. Clearly, we can exploit entropy effects to selectively exclude longer chain alkanes from a mixture with alkanes with shorter chain lengths. However, due to the limited capacity of a single cage of LTA-5A zeolite that has an effective diameter of 11 angstrom, the concept of adsorptive dewaxing is limited to alkanes with a chain length of about NC13, NC14, and NC15. In petroleum industry, we need to be able to dewax by removing the normal alkanes with chain lengths in excess of NC25, NC26, and so forth. For that purpose, we need a zeolite with larger cage dimensions. The all-silica TSC zeolite with a Tschörtnerite framework has the largest cage volume of any known zeolite. This is the unit cell of TSC zeolite. TSC zeolite has two types of cages. This is the LTA type cage with a volume of 743 cubic angstrom. This is the TSC super cage with a cage volume of 2553 cubic angstrom. Here's another TSC super cage, another TSC super cage. See, here's another TSC super cage. The TSC super cage is separated from the LTA cage by windows that have dimensions shown here. The TSC super cage is separated from the adjacent TSC super cage by windows that have dimensions as shown here. Those are the windows shown here, which is somewhat more elongated. This is the adsorption isotherm for NC21 linear alkane in TSC zeolite at 500 Kelvin. I show computational snapshots showing the conformation of NC21 within the cages of TSC zeolite. The saturation capacity is 16 molecules per unit cell of TSC. The isotherm for NC22 in TSC zeolite is shown here. The saturation capacity is again 16 molecules of NC22 per unit cell of TSC zeolite. The conformations of NC22 are shown in these two snapshots. The unary isotherm for NC23 is shown here. The saturation capacity is again 16 molecules per unit cell of TSC zeolite. The unary isotherm for NC24 alkane and TSC zeolite is shown here. The saturation capacity is significantly lower and is just 8 molecules per unit cell. These snapshots show the conformations of NC24 in TSC zeolite. The saturation capacity of NC25 in TSC zeolite also is 8 molecules per unit cell of TSC. And let's now examine how entropy effects can be exploited to exclude longer chain alkanes from mixtures containing alkanes of different chain lengths. I show here the unary isotherms for NC21, yellow diamonds. Blue squares are for NC24. The saturation capacities are respectively 16 molecules per unit cell for NC21 and 8 molecules per unit cell for NC24. For adsorption of a mixture of NC21 and NC24, the configurational bias Monte Carlo simulations for mixture adsorption are shown by the symbols here. For operations for mixture adsorption at fugacities in excess of 10 to the 4 Pascal, which corresponds to feed mixtures in the liquid phase, the mixture adsorption equilibrium is in favor of the alkane with the shorter chain length, and entropy effects exclude the adsorption of the alkane with a longer chain length, because the longer chain alkane loses the entropic battle. For adsorption of mixtures of NC22 and NC25, the configurational bias Monte Carlo simulations for mixture adsorption show that entropy effects are in play if the feed mixture is in the liquid phase, and due to the entropic preference for the shorter alkane, the mixture adsorption equilibrium is strongly in favor of the shorter alkane, and the longer alkane chain loses the entropic battle. So it is possible to selectively adsorb alkanes with the shorter chain length and exclude chain lengths in excess of 24, 25, 26 carbon atoms by adsorptive separation, adsorptive dewaxing using TSC zeolite.